Hello everyone, this is Joshua again, and today we are going to be discussing data visualization in statistics part 2. So last time we left off talking about different data visualizations, the ones we encounter every single day. Whether it's a chart on the subway telling us the prevalence of heart disease in different age groups, or a histogram on some company showing us how many times people use Lyft each week. These visualizations allow us to get to know data with our eyes. And today, we'll dive deeper into data visualization and make all sorts of beautiful graphs and talk about some really extreme situations. Last episode, we looked at a histogram which uses the height of a bar to show how frequently data occur. We can also use this format to make a dot plot. A dot plot takes a histogram and replaces the solid bars which use their height to show frequency with dots. There's one dot for each data point contained in the bar, so we can just count the number of dots to find out how many there are. The dot plot for our olive oil data looks like this. Unsurprisingly, it is similar to the histogram for that data. Or look at this dot plot of how often the sample of people called their moms this month. This gives us a nice way to explore the general shape of our data. But we still lose information about the individual data values just like with the histogram. Occasionally, we want that extra information. Enter the stem and leaf plot. A stem and a leaf plot is a cousin of the dot plot. It also gives us information about the data and their frequencies by stacking objects on top of each other. However, stem and leaf plots use values from raw data instead of dots. So we will turn the olive oil dot plot into a stem and leaf plot. First, we need to split each data value into a stem and a leaf. Stems are related to the bins or bars in a histogram or dot plot. Take our dot plot for example. Each stack of dots might represent a range of 5 ounces from 0 to 4 ounces, 5 to 9 ounces, all the way up to the bar with all the data in the 80 to 84 ounce range. The stem for a bin of data is the digits that all the values in a bin have in common. For the 10 to 14 ounce range, each value has a 1 at the beginning of the number, so the stem is 1. For the 80 to 84 ounce range, the data all have an 8 at the beginning, so the stem would be 8. We can have larger stems too. If the data went all the way up to 2006 ounce, we could have a stem of 200, but that's probably too much for our olive oil example. Now that we have all the stems, we can add the leaves. Each stem, like in a real plant, can have multiple leaves. They're stacked on top of each other so that the height of the stack shows you how frequently the data appear in that bin, just like a dot plot. The actual leaf is the rest of the digits that are not in the stem. If one of our data points is 13 and the stem for that range is 1, that takes care of 1, so the leaf is 3. Leaves appear in numerical order from the stem out. So leaves that are smaller digits are closer to the stem. From a distance, stem and leaf plots look a lot like dot plots or histogram. If you squint your eyes, the leaves almost look like bars or dots. But unsquinting will allow you to see even more information than a histogram or dot plot will tell you. You get to see the individual values and how they're spread out within a bar. Stem and leaf plots are usually flipped on their sides, so that the stems are listed vertically and the leaves extend horizontally. Here's a stem and leaf plot of the number of pieces of the gum each of your extended family has chewed in the last month. Now let's talk about box plots. Box plots use some of our measures of central tendency and spread to visually display our data. A box plot is also called box and whiskers plot. It has two major parts, the box and the whiskers. The box has a rectangle that stretches across the interquartile range of our data from Q1 to Q3. At the median, there is a line splitting the rectangle into halves. If one of those halves is larger than the other, that quartile is more spread out. Since each quartile has the same number of data points, the smaller quartile, the less the spread out that portion of data is. Imagine the difference between fitting 20 clowns in a car and fitting 20 clowns in a regular sized football field. Attached to either end of this box are the whiskers, which help show the minimum and the maximum of all the data, as long as it is within 1.5 times the interquartile range of the median. Its value sets our fences. We use 1.5 times of interquartile range because most of our data will be within this range, especially if your data is normally distributed. Most of the data will be inside the fences. Any outside is flagged as a potential outlier. It can be tempting to think of outliers as data as wrong somehow, but that's not always the case. Values outside the fences are less likely than data near the box plot, but they are not impossible. For example, it's pretty unlikely that if you dial random numbers into your phone, you will call Domino's Pizza, but it is possible. Rare values do happen. Keeping these rare but possible values can be important. When the local news shows you a box plot of local rents and decide that the bottom 1000 rent values are outliers, the graph they display could be misleading. Those rents are the real values that you could expect. Taking them out will make your visualization less informative and might leave you to think that the average rent is higher than it actually is. However, some values that are flagged outliers may not be expected in your data at all. The problem is you may not always know the difference between a point that's valid but rare and the one that's a mistake. Since we still need a way to decide, it is useful to have a preset cutoff for when we discard data. To see how box plots can help us look for these outliers and compare the data from two samples, let's jump to the thought bubble. Justin Timberlake has a new album. This American born singer and a songwriter had quite the career. Our writer, Chelsea, wanted to know how going solo affected the songs he wrote, specifically the number of unique words he used per song. To satisfy her curiosity, she made a box plot for a sample of Justin Timberlake's songs once he'd gone solo, and one for a sample of songs he sang with NSYNC. The first thing we might notice is that the medians are pretty different. The median number of unique words in a Justin Timberlake song is higher than the median number of unique words in NSYNC song. JT has a median of 129 words versus a median of 89 back in his NSYNC days. So it seems that Justin Timberlake may have developed a larger lyrical vocabulary when he went solo. You might also notice that the box part of the NSYNC box plot is a lot smaller. The squished nature of the box plot shows us that NSYNC songs have a relatively similar amounts of unique words. The box plot also shows you some potential outliers to look at, shown by the points that are outside the fences of our box plot. Let's look at a song that's marked as a potential outlier in the Justin Timberlake box plot. The song is Chop Me Up and it has 257 unique words, which is a lot, since the median number of the unique words for a JT song is 129. It is definitely outside the fences. We don't want to throw out data just because it is extreme. And Chop Me Up isn't part of some super experimental Christmas album, so it's hard to tell if this is a valid point. To get around this uncertainty, we apply our preset rule. There isn't one set of rules for handling these extreme values, there are many. For now, we'll use the box plot method and get rid of the Chop Me Up data because it's outside the fences. Remember, statistics is all about uncertainty. I'm not sure if the numbers of unique words in Chop Me Up is just a rare value or whether it's a real equivalent of Neymar in a pickup soccer game. We still have to make decisions. You may have heard of Hank's annual Nerdfighteria census, and while you're interested in taking it, you may wonder how long it takes to fill out. You don't have all day, so you use your new data visualization skills to create a box plot of the data. I can't even see the box or the whiskers through all those extreme values. It looked like some nerd fighters were very thorough or very distracted by other things. 8,000 minutes is 133 hours. This plot isn't wrong per se, but it's not very informative since we can't get much useful information from it. We don't have any better idea of how long it's gonna take to fill out Hank's survey. When you make or see a data visualization, it's important to remember that its job is actually to give you information. If it doesn't do that, it's not worthwhile. Now, let's talk about frequency plots and talk about one last method for visualizing quantitative data, the cumulative frequency plot. Cumulative frequency plots are like histograms, but instead of the height of a bar telling you how much data is in that specific bin, it tells you how much data is in that bin and all the previous bins. That's why it's called cumulative. It's the frequency of all the points we've accumulated up to this point. It's like a small fish gets eaten by a bigger fish, which gets eaten by even a bigger fish, and so on. Each fish is now full of the fish it ate, and the fish that fish ate. Back to our cumulative frequency plots. These plots have their moment to shine when we want to answer a question like how many JT songs have 160 words or fewer. The cumulative frequency plot looks like this. Here's the bar that answers our question. We could also get this information by counting all the songs in the bars that are 160 or less on our histogram, but that's more work. Now that we have seen some good graphs and some bad, we can apply our newfound knowledge anytime we see data visualizations, which will be all the time. Okay, that ends our discussion on statistics about data visualization part 2. I hope you have learned something and good luck.